We'll just wait a few minutes and get started at 7 o'clock here.
I guess we should have had some lobby music or elevator music. I guess we should have had some elevator music. Well, there goes 7 o'clock. So I think we will start. Can you, everybody hear me? Tyler, can you hear me okay? Perfect. I'm not sure how many people have logged in. I think we had about 55 registered. So it's 7 o'clock, so we should start. So again, hello everyone. I'd like to welcome you out to our third online presentation hosted by the Ontario Regional Group of the Institution of Structural Engineers. My name is Nigel Thompson and I am the treasurer of the Ontario Group. If you attended the presentation on the Jeddah Tower, you would have seen our chairman, Alex Hugh, at that meeting. Before we get to the presentation by Tyler Bowman, I thought I would take the opportunity to speak a little bit about the Institution of Structural Engineers for those of you who may not know much about them. The institution was originally founded in 1908 in the UK as the Concrete Institute. Presumably concrete was the most common building material at that time. And it changed its name in 1922 to the Institution of Structural Engineers. One of the institution's values reads thus: we work to create an international community of structural engineering excellence, facilitated by our digital platforms, regional group activity, and networks of special interest. As you can see, it is a group of people who together have a common interest in a specific field of engineering that we hold close to our hearts. Next slide, please. You can see there are approximately 28,000 members worldwide in a total of 105 countries. Here in Canada, we have about 300 members, with 100 or so located in Ontario and growing. Although the institution was founded in the UK, there are now more members located outside of the UK than in the UK. You will note from the slide that for students, membership is free, along with the first year as a graduate. So I recommend any student who may be listening tonight and are considering structural engineering as a career to look into obtaining membership. Next slide, please. One of the benefits of membership is the opportunity to receive the monthly magazine entitled The Structural Engineer, which covers many useful topics and things of interest for structural engineers. Next topic, please. Next slide, please. As I noted earlier, there are 28,000 members worldwide and in many countries. The profession of structural engineering is not an easy one, but it is a rewarding one. The institution exists to help all structural engineers, no matter where they live, to perform their duties in a safe manner and to protect the public. Next slide. As you can see, the institution comprises of the world's leading design engineers as a source for technical resource materials, including presentations like this one tonight, to provide informed opinion and best practice guidance, and provide a worldwide professional qualification that will open doors wherever you wish to practice. In conclusion, I recommend anyone who may be interested in the institution to go to the website and learn for yourself the benefits of becoming a member. With that, I would like now to introduce you to Tyler Bowman, who will be speaking to us about a project that our firm was fortunate to be associated with at the University of Waterloo, the EV3. Tyler Bowman is a structural engineer and partner at WalterFedy. Tyler earned his Bachelor of Applied Science from the University of Waterloo in 2008 and has since established himself as a leading structural engineer in southwestern Ontario. From the invitation to this presentation, you will note that Tyler had the opportunity to work for a contractor prior to starting with WalterFedy as an EIT, a path that provides good experience for young engineers. One of his first major projects was the EV3 edition, and it is a project that some engineers may never get the opportunity to work on or anything similar to in their working lifetime. Without further ado, I give you Tyler Bowman.
Well, thank you, Nigel, and welcome this evening. I'm glad you guys could join us. This is a project, as Nigel mentioned, is one that early days in my career I had the opportunity to work on, and I'm happy to be able to share it with you. I will, apparently I will be having to admit people into this as they come in as well, so I apologize if there's any disruption to the flow. But I want to make sure people get in. I want to start by just talking a little bit, just briefly about WalterFedy here. You know, we're an integrated firm. We have architects, mechanical, electrical, structural engineers, and we have a sister construction company, AEC Development. So we do enjoy working together on full service projects, but we also enjoy working with other architects and engineers and contractors. It gives us the opportunity to learn and grow, get a different experience, and it also provides us the opportunity to collaborate and provide our clients with the best team to deliver the projects that they're looking for. As on this project specifically, so Nigel, who you just met, was the project manager on the project for all the WalterFedy engineering team. He was also the supervising structural engineer, so he sealed the drawings. I was an EIT at that time. So as you can tell, the project goes back quite a ways. It's not new by any means. We built it, designed it in around 2009, 2010. Construction was completed in about 2012. So I'm stretching my memory a little bit as I put this together, but I think I'll cover most of the interesting aspects of the project. The delivery model for this was a design build. So we worked with Cooper Construction, and at the time it was Akitt, Swanson Pearce Architects. I think they've renamed to Pearce McCluskey Architects currently. So they were the architectural team, and from a structural perspective, Telco Steel, that was the fabricator who was integral to the success of this project from a structural standpoint. The building located on the University of Waterloo campus, it was built for environment, the Faculty of Environment. You can see 57,000 square feet. It was LEED Platinum and a construction budget of $18.8 million. That works out to about $330 a square feet. A square foot, I guess. These days, that doesn't that's high for sure, but not astronomical. I think 10 years ago it was quite an expensive building, but for various reasons that we'll touch on. I don't want to miss, I know I'm speaking to largely structural engineers or their team there, but I don't want to miss the fact that this is quite a interesting building from a sustainability aspect as well. It was the first LEED Platinum building on a university campus in Ontario. And in my opinion, it was quite forward thinking for the Faculty of Environment as they work to expand and grow their faculty. I'm going to show a video. It's going to be about 3 minutes here. It was prepared by the University of Waterloo. It speaks largely to the environmental aspects of the building. And then following that, I'm going to jump into what my specialty, structural engineering, the structural systems of the building. So I'll get this started here, and once we're done, I'll dive right into the rest of it.
Hi, I'm Dina Ramsey with the Faculty of Environment here at the University of Waterloo, and we are standing in the Minto Atrium of Environment 3. Environment 3 is targeted LEED Platinum. Now, LEED stands for Leadership in Energy and Environmental Design. Platinum is the highest level of LEED certification and requires 52 points in 6 areas: energy efficiency, water efficiency, material selection, indoor environmental quality, and innovation in design. Solar panels mounted on the roof of Environment 3 produce 67,000 kilowatt hours per year of energy, roughly the amount to power 7 standard Canadian homes. These constructed wetlands increase water efficiency and decrease the load on the municipal stormwater system. Rainwater is funneled off the roof into cisterns below the ground. The water is then discharged into a vertical flow system where the plants act as natural filters, removing contaminants before the water is then pumped back to Environment 3 to flush toilets and water the living wall. This is the 2-story living wall, which is actually attached to the ventilation system. The plants filter out volatile organic compounds and circulate fresh oxygenated air to the rest of the building. The washrooms are equipped with hands-free Dyson air blades and low flush toilets that use gray water from the constructed wetlands to increase water efficiency. These steel trusses give you a really good idea of how Environment 3 was actually constructed. In order to keep the physical footprint as small as possible, the foundation for Environment 3 was poured right next to Environment 2. Then these giant steel trusses were constructed on site and suspended up and over top of Environment 2, straddling the existing building. The 3rd and 4th floors of Environment 3 were then built on top of the trusses, making them structurally independent of the building below. This is one of the kitchen areas for faculty and staff, and here we have a really nice example of some of the sustainable materials chosen for this building, including rapidly renewable bamboo, Forest Stewardship Council certified wood, and linoleum, which is made from linseed oil and other natural products. This is one of 2 skylit courtyards in Environment 3, and in fact, 90% of the spaces here have access to daylight or natural views. Daylight sensors in the ceilings also automatically adjust the lighting loads, increasing energy efficiency. These experimental rooftop gardens off the 3rd floor patio were inspired by a student design competition and will act as a living laboratory for students in the ecology lab. They're planted with native drought-resistant species and require no additional irrigation. Williams Fresh Cafe is a food vendor in Environment 3, serving locally sourced food and fair trade organic coffee. We'll end our tour of Environment 3 up on the 4th floor with one of the best views on campus. We hope you enjoyed learning about our LEED Platinum targeted building and its many green features.
So that's a video you can, I think it's still on their website if you want to go back and revisit it. They mentioned LEED Platinum targeted. It has been certified a building as a LEED Platinum building. I thought I'd touch on a few things as well, just about the procurement and kind of where we started and where we finished and at a high level. So it was a design build. The RFP requirements asked for LEED Gold and upgrade. I think LEED Silver was the base with an upgrade to LEED Gold. Throughout design, a significant donor came in and said, if you can get this to LEED Platinum, they'd be willing to put some money into it. So, you know, we had some changes along the way. They didn't impact structural too much, but definitely some other systems. They started at $12.5 million, and we finished at 18.8. Now, I think to be fair, I'd have to, don't quote me on this, but when we submitted our bid and were awarded, I believe we were in around the 14 or 15 mark. So I don't believe it ever hit the 12.5 million, but it did go up, you know, a $210 a square foot compared to the 330, and we were slightly under in their square footage, but they still got the programming that they were looking for. So you can see that through. I don't know if I've ever been involved in a project where when you start, you end up exactly where you thought you would. This was definitely one of those situations. And I believe the client, the university, got a pretty awesome building for what they and met what the expectations they were looking for. So going into some design considerations. Now, this was 10 years ago. When I opened up the folders and the files, I was looking for all the cool pictures and the 3D modeling, but you have to realize that in 2009 we've come a long ways from there with our BIM and Revit and so forth. So this slide here is to mostly show that, you know, a 150-foot span was not the only challenge we had right away in our pursuit. The green is the existing Environment 2 building. The orange is roughly where our footprint we could work within. It was allocated by the university master plan to the Faculty of Environment. So they were trying to work with what they were provided from the university. In red there, and the brick building in the picture there, that's the mechanical penthouse that was on top of Environment 2. And then you can see the large air handler units, mechanical units on the roof where it's shown in blue. You know, looking at it, you could say let's knock those off, but the building had to be occupied throughout construction. It was needed for the courses they were offering. And it was, and so to look at that and say let's temporarily relocate these services would have been quite the undertaking from a mechanical or a cost perspective. So right away we had some, not just a two-story building, but some challenges or opportunities to find some solutions there with the rooftop equipment and penthouse. The building, as it was built, is a cast-in-place building. The Environment 2 building, cast-in-place concrete, was built in the 1980s. So first, I'm not sure where it went, but Nigel did, and I looked at what would it look like to reinforce this building. You know, it's worth exploring, but pretty quickly it was ruled out. There are lots of challenges with reinforcing a cast-in-place building. More challenges when you're looking at doubling the height and having it occupied during that construction time. So that was ruled out fairly quickly. With that said, the architects worked out a number of a floor plan here that we could work with. We could work around those rooftop units, that penthouse, and you can see on this slide, the yellow areas on each floor are the open to, well, skylights were above these areas. So the four-story atrium, and then on the fourth floor, the out courtyard areas. The orange there, you can see there's some renovations to Environment 2 building, nothing overly exciting from a structural perspective. And then, as you can see on the third floor, the architects worked some magic there, got a layout and a program that worked for the University of Waterloo. And our challenge from the structural perspective was to work around that with our structural system. We did have minor section of, I believe, the penthouse demolished, mostly where they had some offices for maintenance and so forth. So we made it slightly smaller so we could get some more footprint from the west side, which is the bottom of the page there. I think what most of us who have been in the industry for a long time will realize is that you need to read your RFP well. I lost some sleep. I remember it quite vividly. I lost some sleep over this. After we were awarded the project, I think probably Nigel pointed out that the minimum live load was 4.8 kPa, which is a higher load than the building code would say you have to have in office locations and so forth. So I remember getting up early, going into work, looking at what I put into the model, the preliminary model, and I did carry 100 pounds a square foot, which I was kind of surprised because I recalled thinking I need to kind of optimize this with our office loads and different occupancies. Typically, it might not be a significant issue, but we were carrying a lot of load on these trusses, and that could have been quite a significant issue, having just been awarded the project. The structural system that we chose to pursue was a structural steel brace frame building. You can see it largely put together there. I don't think, we didn't have the roof deck on in this photo on the top left. And we had some floor decking to put down over the suspended portion of the building. You can see a little bit in there. We chose to put a guardrail height parapet on this building, so you can be on the roof without any fall restraint systems. So you can see the framing going up there. Out the front there, there's a pretty cantilevered canopy section that was another challenge. The jumping into the floor framing, it's probably the least exciting part of this building, but it was something we spent a bunch of time exploring. During the pursuit, working with Telco, we explored a number of options, open web steel joists, composite beams, different deck sizes. The challenge we were running into is we had to match existing floors in the Environment 2 building, which was a cast-in-place concrete building. The floor system, the depths were quite a bit more shallow than what we could achieve with structural steel. And then we as most architects like, and I enjoy being in buildings with high ceilings as well, creating more of an open, inviting aspect to the building. So we were trying to raise those ceilings. We had mechanical systems, as we all deal with from a structural perspective, that want us to crunch our structural systems. We looked at different spacing or different deck spans, 1.5 inch, 3 inch. We ended up falling on actually Can-Am's 2-inch deck. Gave us, working with Telco, it gave us a cost-effective span to wait for our beams and depths worked out. We did look at what a composite beam system would look like, but putting the studs on all the beams was pretty cost prohibitive as we were pursuing this. We did go with down. You can see what this is trying to show is I'm pointing at the composite girders in the isometric view down below. The red beam lines there are where we did go with a composite girder system. Twofold, we were carrying more weight. We had to bring those shallower as well. And then at the same point at the east side, so kind of the top side of this, we were spanning over a tiered lecture hall. So we didn't have bay spacing. We basically lost a column so that we could have an open space. We looked at introducing a column in the second to third and fourth floors as well, but it quickly adds depth to that first floor beam. So we carried that system up the multiple floors there. Really, it ended up being that we had to tie into a second floor of an existing building that was a different structural system. So we worked through that. So as I mentioned, we didn't have all these ISOs. So one of our talented technologists at WalterFedy put these together for me fairly quickly over a day to help me describe what would have been quite challenging if I just did 2D CAD drawings. Going to the foundation design now, saying it's challenging soils is maybe a little may not be the right words, thing to say in terms of conventional spread footings, shallow foundations were quite reasonable. I've seen it wasn't great soil, but it wasn't the worst I've seen either. The challenge was when we were trying to pick up the significant loads from the suspended portion in these soils and keeping those foundations close to the existing building was interesting situation or challenge. We ended up going with a CFA pile, but we had explored micro piles. Looking back, I think I might have spent a little more time looking at the micro piles. It was challenging to get them in a pile group that would get our structure close enough to the existing building. But as you can see, we also had challenges with the CFA piles. But from a cost perspective, this was where we landed with Cooper. You can see there's multiple pile groups in pink there. So the two of those had 9 piles, 2 of them had 8. And then in between, it's showing one, we actually had 2 piles in each of those smaller sections. And then to make sure that we didn't have any differential settlement issues, we made sure all the suspended portion and anything, or the stair tower, I guess, on the top right there as well, we put it on piles. We wanted to make sure that we weren't going to run into issues with that portion settling differently than or with amongst itself. The 4-story piece wasn't as critical. We worked through some details there to make sure it was okay. For those of you who don't know what CFA piles are, the continuous flight augured piles, this was the first time I've used them, and I haven't used them since. I've explored using them on some projects, and they do have their uses. We use this as end-bearing pile solution. It wasn't, there will be some shaft resistance and interaction with the soils and the concrete, but it wasn't assumed to provide additional capacity in our design. Ultimately, this description here, or this picture here, shows you auger a pile with auger down to the design depth, and then once you hit the design depth, you're withdrawing the auger and you're pumping in a grout concrete mix down through the shaft of the auger as you retreat the auger, ultimately filling the augered shaft with concrete grout, and then you end up with a pile. Once the auger's out, you're putting in the reinforcing that's required, vibrating that down to make sure it gets in there and it's consolidated around it. On site, this is what the drilling rig looked like. Our piles were 20-inch diameter. They were a 30-foot depth. And then we had to space them out 2 or 3 times the pile diameter, which keeping that tight to the building created some challenges. You can see in the top right photo there, though, the drill rig could get quite close to the existing building, and then we didn't have to add any lengths to that drill. I believe that drill there is about 30 feet. The auger attached to it, so you can see the hose going up that would pump the concrete into the augered hole, and then the reinforcing cages there. You walk out to site, when it's cleaned up, you just see this 20-inch round dot of concrete. And then that's ultimately what you see, and it's quite impressive. They move pretty quickly along here, and then we put it together. So we had 9 of these to go in, and we had to space them apart. So we ended up with a pile cap, or a large grade beam that you can see there. We were looking to get depth for our stiffness. We didn't want to overload the piles directly below the column. So we were looking to get as much depth and as we could to get across that whole pile group. For sure, you're going to load the center piles slightly more than the exterior, or until you get a settlement where it equalizes the loads on all those. But we put that together. In the middle, there are 2 columns in the middle. You'll see shortly that it was our brace bay for the suspended portion. They came down on two piles, and then what ended up happening, we ended up connecting those together. So the large pile groups with the smaller ones with a concrete grade beam. That was largely or solely for engaging all our piles in for our lateral loads from the brace frames. We had to engage them all to provide enough. Ultimately, we drove bending into our piles, and so we needed most of them to be able to resist that. You can see a little bit in the one photo. The insulation, we put insulation against the foundation wall to provide that break from the existing building and our new structure. Nigel and I talked, I remember talking about this quite a bit, and we ended up asking for a load test on these piles. We managed to set it up where we had two sacrificial piles, the test pile, and then we found a way to maneuver. Well, we didn't. Deep Foundations found a way to maneuver the test rig in, so we could utilize 2 of the piles that we were going to use for the final building. So they installed those, connected the testing beam to it. We did not load to failure. It would have been interesting, but the concern would have been that we'd be pulling up on 2 piles, putting them into tension, which they weren't necessarily designed for, on 2 piles that we were planning on using for the main structure. I don't recall exactly the testing criteria we looked to do or to use, but ultimately, it was tested. We buried those other piles and we got the information we wanted to have. Oh, sorry. Here we go. Nope. So getting into the superstructure above grade, the isometric there you see is really it's highlighting our braced frames. On the 4-story section, we had 3 with a 4th working with us too. And then we had the 1 braced frame at the south end or the top end of this photo. It worked well. We used the 4-story section of the building to really take the lateral loads in the one direction from our suspended section of the building. And we ran into some interesting pieces. So the floor, the deck, concrete on deck was our diaphragm for each level. But if you look at the 3rd floor, we have giant holes throughout it. That created some challenges to get the diaphragm loads into some of our braces. So you can see where we have the cutouts. In blue there is largely the deck. We have the red or the yellow, sorry, the yellow section, which was the atrium. And then you can see where we have the cutouts for the penthouse, rooftop penthouse, the existing one, and the existing air handling units. So we worked through it, and we managed to get our diaphragm loads through those kind of pinch points, and we did it kind of a belt and suspenders way. We looked at the deck and the fastening and the concrete, and then we did plan bracing as well. We did it in the section you see there where the existing penthouse was, and then across the four-story atrium on the top and bottom sections there. So it was a challenge, but we worked through it. Like I said, we were added some bracing just to help us be confident that it was going to work and didn't just rely upon the deck and the concrete. This is the part where it gets interesting. It's not a building you get to do every day. The section over the existing building we kind of described it a little bit in our flyer for this presentation, but we ended up two main trusses. They're 150 feet, 33 feet deep, and they sit the top chord bearing on columns on both ends. We tied that together with five secondary trusses. Now these trusses were one story high, about 15, 16 feet, 100 feet long, tying into the vertical elements, vertical web members of the large trusses. And we had two different types of truss there. The two different types were twofold. The center green truss there is picking up more tributary width. The bays were larger there, and then we also had the penthouse to contend with. So it was slightly it wasn't loaded as much from a third floor perspective, but we also had a column or a hanger that was offset from the panel point. So we had some bottom chord bending in some of the members. So that was the main reason we had two different truss types. As well, I guess what I didn't elaborate here either, the secondary trusses actually we have the third floor hanging from them. So there's nothing, I'll touch on one thing, but really there's nothing touching the existing building. We had space on the exterior, on the wall sections, we didn't connect in there. And then we had a gap above the roof as well. So although when you look at the finished building, it looks like it's all tied in and it's one nice building, it looks good. From a structural perspective, I wish they had a giant gap and you could see the building suspended. But that wasn't where we ended up going. So the building is fully disconnected from this, including the stair tower on the north, disconnected from the existing Environment 2 building. Now, getting into some pictures here. So the main truss, I don't know if Telco Steel was ever a part of this conversation, but when we were pursuing the RFP internally at WalterFedy, we looked at it and we said, well, how are they going to ship a truss that's 10 meters tall, or sorry, 10 meters tall, 150 feet long to the site? And so we actually explored a couple different scenarios. We kind of looked at it and said, well, what if we do both floors independent? So we have a long, shorter truss, but we don't suspend the third floor off the secondary trusses. Quickly, you run into challenges. On the third floor, we got that existing penthouse to deal with. The trusses are pretty shallow compared to their span, and you're contending with some significant deflection challenges. And so we ruled that out, but then we also looked at, well, what if we ship two 150-foot trusses, 15 feet high, and we connect them, and bolt them, weld them, whatever that connection. It gets really complicated. There's a lot of loads going through those connections. And then ultimately, we ended up talking with Telco Steel, which we might have started there to be looking in hindsight. They said, you know what, we're going to build it on site. Well, and so Telco has a large enough shop, Telco Steel, that they built this in their warehouse. So before they shipped it to site, they assembled it. They made sure that it fit together, that when they got onto site, everything was going to work. And then we had to go convince the University of Waterloo that we needed to shut down Ring Road, they call it. It's their main road. It does a big ring around the campus. And we just interrupted that for a section of it. So I don't think that was a hard conversation. I wasn't a part of it, but they understood. And then Telco, they erected this horizontally, and they lifted it into place. I'll show some erection photos there as they put it together later on. Secondary trusses. So these photos as well, that they're a mix of the architects, of WalterFedy's, of Telco Steel's. I pieced them together from some flyers and awards pamphlets and some of our marketing material as well. Quite interesting photos. I like the one on the bottom left specifically. It looks unique. It looks interesting, and having designed it, I'm quite proud of where it ended up. This was the 5-meter high trusses, the secondary trusses. The roof was open web steel joists. We did tie it together with some beams as well to stabilize the top cord in its weak axis there. Bottom cord bearing truss and they framed into the vertical web members of the secondary trusses. You can see what it looks like, and you could go well, maybe not now, but once things open up a little bit, hopefully within the next year, you can go see this yourself. The most of the trusses are visible. They protect them with fire intumescent paint, and then you can kind of see how it goes together. I put this picture on the left of the connection design on here. Just as I went through it, I realized that 10 years ago, a lot of this stuff wasn't, 10 years ago, there was definitely programs that we used to design connections and so forth, but not everything. We still had a lot of things we were doing hand by hand sketches. When I looked through the design notes, I had so many details sketched out on graph paper to give to the technologists, and it's something that's not, we found better, more efficient ways to do it, I guess, but it brought back memories as I went through it. You'll see here the top photo there, that's a tension splice in the bottom cord, I believe, and then as you go around, they're big connections. The photo in the center there with the chalk on it, something that I picked up on site when I was looking at the truss connections. It's maybe a little difficult to see here, but on the bottom part there, it's the plate is prepped for a full penetration weld, but the weld was only partially filled. I remember bringing it up to Telco, the fabricator, when they were on site one time, and they commented that, and recalling the conversation, there were so many iterations of trying to optimize this truss, and it takes time. Time was minimal, so Telco actually started moving forward with some connections, and once we got to the final loads that these nodes and these members were going to get, they had plates that were fabricated that were thicker than required, and so instead of throwing them out and reducing it, they used them, and they saved some labor by not having to do those extra 10 or 20 passes on a ton of weld, or a ton of connections. So I guess the point being there, it is a team effort. It's not the fabricator, it's not the structural engineer, it's not just the architect alone. When you see something, ask questions. It could have been an issue. It definitely wasn't. but it would have been a significant issue if it was put together and that was incorrect. So point things out, bring it up, ask questions. It's better to do that than it is to move forward thinking that it should be done correctly, although it was. Looking at another aspect of this, the green roof. The green roof was definitely a sustainability feature, but it came about largely because we're building a two-story building on top of an existing one, and with that comes snow drifts, additional loads on the existing structure. So the way and this is where I guess I said we didn't connect anything to the existing building, but we did connect these snow shelters. We looked at the existing roof, we had the existing drawings, cast place concrete, knew what the bars were in it. It was in reasonable condition. We had a look at it. And we found that with an increase of snow drifts loading, we weren't going to be able to, the existing roof wasn't going to be able to deal with it. It's on both sides, so you can kind of see the red on that photo there and at the top of the page. That was just roofed in, but on the close side there, on the west side of the building, it was turned into a green roof and a patio. We looked at columns and foundations, and we found that we could stub up an HSS post off our columns. They had enough residual capacity. We were removing some loads, and so we did that. So this was kind of a snow shelter, so that we didn't load the existing roof. And then there's a bay actually closer where it steps down that we did do a green roof there as well. It's the end bay of a cast two-way slab. So we did have to be mindful that we were removing load from that the existing roof was going to see for most of the building. So then we were adding a bit of weight from a green roof perspective. I believe, and again, don't quote me, but I believe from when the design loads from a snow climatic data standpoint were slightly less in the current building code at that time than they were when they were designed. So we had some residual capacity there that we worked with, as well as just a pure look at what existing building conditions and design and work through that. So it creates a nice, aerial view photo as well, and it creates some open space that they mentioned in the video that the university uses as a teaching space. Some of the interesting photos from a truss perspective, installation perspective. You can see the bottom left photo there. That's a column splice. We did splice the columns just above the third floor. We might have been able to ship them, but they were getting pretty long. So we did reduce the section slightly. It's a welded wide flange actually that we ended up going with on the suspended portion in the four corners. And then you can see them bolting it together. The picture with the lift there in the top right is the top cord bearing connection on this column for the large truss, and then the one the large photo there bottom right is them actually. So they've installed the one truss already, and they're lifting the second one. So they had a three crane setup to lift these. They actually had to lift the one on the far side that's already installed in that photo. They had to lift it and then pass it between two cranes. And so you saw the riggers up there. They were trying to load the one crane and unload the other crane and pass it over. There's another photo coming up that'll show a bit better. The mobile crane there. Was there you can see actually the bend in that top cord and the weak axis. So that was why that crane was there. I think it was a little behind at this point, had to catch up in lifting. But that was to try to really reduce stresses on those connections that they weren't intended to see in its operational life. Or the truss, this, some more photos. You can see the one the 5 meter high truss flying through the air there on the bottom left. They're setting in the second truss in the center photo there, and on the right, that's the kind of 3 crane setup. So the 2 white cranes there had to pass the truss to get it to the far side. This actually went surprisingly well. I don't know what the contractor and erector were saying, but this seemed to go together like a glove. To give Telco credit, I didn't see anybody trying to get some alignment bolts in there that didn't fit. All the trusses put together, the secondary trusses aligned well, were connected, and it was all put together within a day. The only hiccup actually was everybody showed up to watch this on the day they told us it was going to happen, and the crane in the bottom right there, the one on the right of that photo, broke down. So it wasn't working. So everyone went home. They fixed it overnight. We went back and they put it together and during that day. From my perspective, we're coming to the end actually. If you have any questions, please feel free to type them in the group chat there. I'll try to answer them. I should have said that at the beginning, but please feel free to add them there, and I'll get to them after this slide. From my perspective, if you design a building or a structure and you walk away from it having not felt you learned anything, I think you're missing out. Lessons learned is a critical piece to what WalterFedy strives to do as well. Every project has unique challenges, but because of that, there's unique solutions. And when you work together with the team, with the other engineers, with the architects, with the contractors, there's always something to learn. Lots of positives. I'm going to touch on some of the things that 10 years, 12 years later in hindsight, seem kind of intuitive, but as an engineer in EIT at that time, that was about 1.5 years or 2 years out of school. I took away these things, and my team probably hears me bring them up fairly frequently. So the main one that you won't see very often is we had some larger than expected deflections in those 2 main trusses. We did ask for a camber. Now we asked that not knowing how that would be achieved. Telco largely achieved that. It wasn't a true camber, but in their connections, they managed to take that top cord and bottom cord and crank it slightly to get our cambers. I think we asked for 4 or 5 inches on the large trusses. I haven't tried it, but putting this together, I feel like I should go to the building and set a marble on the one hallway that runs the length and see what happens. I haven't heard anything that would cause from anybody that it seems like an issue. But it did come out under the dead load. We ended, and the way we actually found this out is because they were putting a curtain wall in that along the face of the long truss, and that is definitely square, and our truss has a deflected shape. So when the curtain wall installer started putting it in, they ended up shimming it in the center. I'm going to say about 1 inch or 1.5 inches, just so that they had enough deflection head at the top. But then at the 2 far ends of the truss, at the column supports, they ended up running into the concrete. And so the contractor chipped out some of the concrete and got that curtain wall in. But definitely the camber came out under its dead load. And we probably had 1 inch or 1.5 inches more that we were trying. That might be extreme. We might have ended up with 1 inch that we had to deal with when we were installing some of the building envelope systems. The The secondary trusses worked well. I didn't see any issues. We asked again for a 2 or 3 inch camber in those, and it worked well. The photo that I have on the bottom with the foundations there, take your columns to the slab on grade, and especially your brace bay ones. This was a miss. The architect on my part, well, lack of maybe a bit of experience. I have a brace bay with a pier that's sticking up quite a bit. I had to design that pier so it could take the bending, get it into the foundation wall. But as well, this was in our lecture halls area. So that is that wall there where the column is actually our brace, or is the back of the lecture hall where, you know, you got your screens, your chalkboards, or whatever. It feels tight, and then because they had to fur out around that pier, they probably lost another 6 or 8 inches. That they had to bring out that wall because I didn't take that base plate to below the slab and get rid of that pier below the slab. So if you can, take them down to the slab on grade levels. The other piece, you can see that exterior X-brace section there. Those were exposed X braces. The architect wasn't happy again when they installed those and looked at it. We got the tube right. We didn't go with a double angle or something like that. But the connection in the middle it's a standard connection. It's a plate through the tube, and then the 2 shorter sections. But it's not really the nicest look. So if you have exposed connections, make sure you take the second look at the shop drawings. You make sure the architect's aware of it. The steel beam through the 2-story green wall. Another thing that the architect pointed out and asked me why that beam was there. It's needed for the structural system. There would have been other ways, probably fairly expensive ways to get rid of it. But it didn't even cross my mind that there's a beam going through the 2-story wall or green wall. And then the last thing, I guess, on here, it would be the grade beams. So those large pile caps and grade beam over my pile group had significant rebar in it. We had 2 layers of 30, 35 M bars in the bottom. I hooked all my bars to get embedment. I didn't likely need it. And it was a nightmare to get both layers hooked with the hooked bars on the end. To get them in, I believe Nigel came back one time and from site, having heard a mouthful from the rebar guys, reinforcing steel, and said, "Do we need it all?" We looked at it, and they ended up cutting a bunch of the hooks off the second layer to make it go together easier. Few things I missed, nothing overly exciting, I guess, nothing that. But I always look to take something away and take it to my next project and look to make sure that other people can learn from my mistakes as well. So I thought I'd share those. But this is largely the end. My next slide is questions. I haven't seen any come into the chat as of yet, and we're coming up on 8 o'clock here. So I don't, if anyone has some, please jump in, type them in, but I appreciate your time. I hope you learned something. You saw something unique and interesting. I love, this is a building that I haven't done again, but I have seen RFPs and we have pursued some. I think one was at McMaster. It was a similar 1-story building, existing building. They wanted to put 6 or 7 stories above. You know, it minimizes the building footprint. It keeps the existing buildings. If they're in good condition, why get rid of them if you can keep them? So it's something that has been done. I think it's probably currently being done. We didn't get that project, unfortunately. However, we'll likely be pursuing some more like that in the future as people try to maximize the space on their properties and campuses. So I'm going to stop it there, I guess. I haven't got any questions from the group chat here. So I think we'll end it. Thank you again. And I don't know, Nigel, if you're looking to touch on anything, feel free to jump in to end this as well. But I'll go ahead.
I think you did a great job, Tyler. It brought back memories from when I was working on it with you in 2009. And as you say, learning from your experiences, we all do it, no matter how old we are in our, excuse me, in our careers. There's always something you can learn. And then for us older engineers, we have to be mindful of passing that information on down to our younger engineers, because we don't want our younger engineers to fall through and make the same mistakes as we did. And maybe I could have done a better job with some of the points that you raised, but it's something we need to be mindful of in our professions. We're only as good as the people coming after us, and we want to make this a better profession. We want to make it safe and reliable for the public, and we all can have a good, restful night, not have to worry about it. So anyway, again, thanks very much, Tyler. I certainly appreciated the presentation. It brought back memories, and we look forward to the next one. And anybody out there that say, check the institution website for more information on it. And any graduates that may be out there or students, I encourage you to consider becoming a member. It's something, if you're not going to stay in Canada, it's definitely going to be worth your while. And even if you stay in Canada, as I say, there's opportunities to learn from others, especially those in the institution. And look forward to talking to you if you have any questions coming up. Okay, thank you. Thanks, Tyler.
Thank you.
Bye-bye.